Now, before you can actually put this network to use, you need to train this network. Now, for the sake of simplicity, we're going to take an isolated and a controlled example. In this example, we're only going to train the network to classify the number one, and we're going to feed small data sets as input in each iteration of training. Let's begin the training. In the first iteration, the parameters, the weights and biases, that is, are randomly initialized so that the network starts to respond. So you gave it an image and let's see how it responded. And there you go. It thinks that it is a 7, which is not a bad thing. So just to keep in mind that in the first iteration, the weights and biases were randomly initialized. So let's calculate the error. So the error is desired output minus network's guess. You wanted the network to guess 1, but the network guessed it as a 7. So the error is 1 minus 7. Let's not really worry about the sign here. We want to take the absolute number here into picture. And the network's goal is to reduce this error to a 0. So when this error is a 0, that means the network guessed it as a 1 and you also gave the input as a 1. Now what the network has to do is to adjust its weights and biases proportionally to their contribution to the error, and in a way that it reduces the overall error. Now let's take a closer look at how the network goes about achieving this in an optimized way. So that was the error for one specific guess concerning one specific sample. Now you want to convert this error to a loss function or a cost function. There are many functions available. One such is mean squared error. So you basically square the error and take the mean of it. The two here is to simplify the calculations. Now keep in mind that this function is also differentiable, which is very important for the next steps. Let's try to simulate this. First, let's establish what we are going to do. So this is the first forward pass where the parameters are randomly initialized. This can also be called as the first epoch. In this dataset, we have 14 samples. As you can see, sample 1 through 14. And all these samples are of the number 1. To simplify this example, I'm just going to feed the number as it is in this simulation. So we have the input as 1, weights W are random, and bias B is a constant 3 in the first pass. The output function is weights into the input plus the bias B. Alright, now we have some context what we are going to do. Let's take a quick look at the table here. So we have one column for sample, one column for weights. I am using a function called random between -10 to +10. So this randomly generates number between -10 to +10. In the output, we have a simple calculation which is weights into the input plus the bias B. So if I go to the cell, actually you can see 1 is the input, H6 is the weight, and 3 is the bias. The error function is the desired output minus the network's guess. So if I go to the cell, you can see that I'm taking 1 as the desired output and minus the network's guess, and I'm taking the absolute value by using a function called ABS, and I'm passing the network's guess. Error squared is simply squaring the error, and I'm using some data manipulation to make this column look good. I'll make this sheet available so you can play with it and try for yourself. Alright, let's get started now. So the first sample comes in, and this is weight 3 multiplied by weight 3. See, the output is 6, so the error becomes -5. 1 minus 6 is minus 5, and the square is positive 25. So you do that for all the 14 samples. So this is the first epoch, and then you get the total error as 504. You get the mean squared error. So there you go. Now you have the mean squared error for the first epoch. Now the network is going to go through many epochs, and using a function called gradient descent, this is an algorithm. It uses the partial derivative of your loss function, and it finds the minimum of the function. So this is where your error is going to be 0. Now if I go back to my sheet 1, we can see in some spots that the error is actually 0. Okay, now let's go and simulate gradient descent. So here what we have is we have different epochs. So these are different times consisting of different data sets in the training phase. So in this sheet, let's try to discuss the gradient descent algorithm's approach in reducing the error. Now first what will happen is it will go through many different epochs. So here we have 16 epochs, and we have the cumulative parameters, and we have the cumulative error for the gradient descent. Now the gradient descent will understand this pattern by taking a partial derivative and applying its own algorithm and trying to ping pong and finding a minimum for that function. So this is just to take an idea. This is the error for the different parameters. Now once gradient descent has significantly understood this sample of data in epochs and the error, it will be in a better position to advise the adjustment of weights and biases. So in this sheet we see a little bit better approach for the gradient descent algorithm in reducing the function. So here we also have a set of epochs, we have the cumulative weights, and we have the absolute error. But this time let's assume that the gradient descent has a lot of samples and some time to train itself and eventually the network. So what we see here is on the epoch number 4, we have cumulative parameters as 3 and the error is 2. So this is the local minimum. So for example, if you take a ball and if you roll the ball down here, the ball is going to rest in this local minimum, and then eventually the algorithm will find the major minimum, which is here right about when the cumulative parameters are 1. Eventually the algorithm is supposed to find the major minimum or the average of local minimums, which seems to work out as the same as the major minimum. Now we have somewhat of an idea as to how the gradient descent performs, or the approach of the gradient descent. Now keep in mind that we're only discussing about one neuron, a limited data set, and a limited number of epochs. So as the number of neurons and the hidden layers increase, these calculations are highly untraceable. And imagine the number of parameters the network must be handling. Each hidden layer will have a cumulative error. Now based on the quantum of error and based on the gradient descent algorithm, each of these weights and biases need to be changed proportionally in order to reduce the overall error. Now in order to do this efficiently, the gradient descent uses a method called back propagation. In the next video, let's take a look at that and finish this example.